This is a video about potential energy. Now, where kinetic energy was energy due to motion, potential energy is going to be energy due to position. And I talk about this a little bit in the document. The idea here is, if we have some kind of energy that can become kinetic, then that will be potential energy. So maybe I am standing here and I have a block and I'm holding it out. When I let go of that block, it's going to start falling. Now right now, it's not falling yet, so it doesn't have any kinetic energy. Once I let go, it starts falling, and it'll keep speeding up and speeding up as it moves farther down. You know this already. If it keeps speeding up, and my kinetic energy, if you remember, was half mv squared, then as it speeds up, it's gaining kinetic energy. That kinetic energy has to be coming from somewhere, and that somewhere is potential energy. So potential energy is going to be energy due to position. We have a handful of different ways that we can get potential energy. We can get potential energy from gravity, that's the one we'll do the most, from any kind of elastic force, and then from different fields. And we'll do fields a little bit later in physics 2, really. So for right now, the big ones that we are going to deal with will be gravity and elastics. Gravity we have previously already split into two scales, and we're going to stick with that. So what I'm going to call small gravity versus big gravity. Small gravity is going to be anywhere kind of near the Earth's surface, and then we're going to get a potential energy function that looks like mgh. Now looking at this thing, if I've got this block and I hold it 1 meter above the ground, and maybe this block has a mass of, let's go 2 kilograms. I could say that this thing has a potential energy of mgh is 2 kilograms, 10 meters per second squared, 1 meter, 2 times 10 is 20 times 1. That's 20. Got kilogram meter per second squared. That's a newton times a meter. That's a joule. So 20 joules of potential energy. But what if I'm holding another block, just like the first, and this one I happen to be holding off the edge of a small cliff. Maybe that's 4 meters. What do I do now? This thing I could say has a starting height of 5 meters, that's fine. But then going back to that first one, is that really 1 meter? If the ground is all the way down here, that's not really 1 meter anymore. It doesn't quite work the same way. It turns out that what matters with gravity, what matters with this potential energy, isn't just what that h is, it's relative heights. So I want to find how my potential energy changes as I move from one location to another, which means there's not a spot that I have to call an absolute zero for potential energy. If I'm doing a problem and the entire problem is going to take place up here, so if I'm doing kind of the right half of this problem, I'm going to say, you know what, let's have this space right here be my h equals 0 and measure things off of that. If I'm doing this problem here over on the left, then I'm going to say, let's let this space be my h equals 0. And it doesn't matter which one I use, I just have to stay some kind of consistent with it. So for a small scale, my potential energy is mgh, and it doesn't matter where I call h equals 0. For a big scale, my potential energy is going to be, you remember m over r squared? It's going to be negative gmm over r. Here's what that negative is about. If I have a graph of energy versus r, this negative gmm over r is something that's going to look like that. And this makes what we call a potential well. If I've got a total energy right here, what that means, it's kind of like having a ball that's in this location. That ball is going to roll back downhill. It's going to go back closer to an r equals 0 location. So what I have with this potential well is anywhere where I place an object, in this case I'm probably placing a planet, anywhere where I'm placing my object, it wants to be pulled back in toward the source of this potential well. Maybe it's a star, right? Maybe this is the sun. Wherever my planet, wherever my object is, it wants to be pulled back inward. The only way that I'm getting out of this potential well is if I'm infinitely far away and that energy becomes 0. This potential well, because it's a gmm over r, negative gmm over r, the farther out I get, the flatter that becomes. So if I start to put an object way, way, way out here, it's not going to accelerate very fast at all. But it'll slowly inch its way over to the left, keep speeding up, till it gets to this point, speeding up more and more. I get this potential energy function that looks like a negative gmm over r. Not a big deal. R is the distance from the center of the thing that's producing this potential well. So maybe the distance from the center of the sun, for example. Elastics. We had this force equation that was equal to, we had a force was equal to a negative k times x. We're going to have a potential energy that looks like a half k x squared. I will give you a second video that works through different examples of this so that we can calculate potential energy for these different functions, but these are kind of the major sources of anything that we will be using for a while.